So yeah.
Can you explain quiz 9, question 17?
Quiz 17. Oh, hopefully here. This one? Okay, great. Okay, so the angular momentum quantum number. So all of these for that valence electron in sodium, and in this particular case, I gave you, I would consider it an easy one because you only have one electron in the valence shell. So it's that one s that s electron, not one s. It's a 3s electron in the ground state. So in the figure caption, it says the column labels of the energy levels are this right here. So these are the labels. So I went ahead and I put them down here in red. So this column is P6NS. The P6 would be from sodium, the previous P6, so neon. So that's another way of saying the neon core. So this is the ending part of the neon core. That's just the way the atomic spectral database puts it out there. I can't really change how they present it. But we would put, neon core NS1, and this would be the 3s, and state 2 would be the 2s, no, 4s. And so then this whole column is NP. So this is where we get the angular momentum quantum number. So that's L. And L can be 0, 1, 2, 3, all the way up to n minus 1. That's the full set of L's. And that's where the S, P, D, F, etc. come from. And so since we're in a P, it's 1. So it should be this one here. So that's, yeah, so state 4 is an excited state. Now, we know it's a p orbital, but which one is it? Like if I asked you to give me the electron configuration for number 4, what would we do? So we see this as a sodium atom, so that we can look at the periodic table and kind of get the ground state electron configuration. So sodium's right there. Without even writing anything down, tell me what noble gas core we have. Neon, that's the previous one. And then we enter the third row, so that's the 3s. So it's neon core 3s1. So let me just quiz you. What's the first available P shell? Why do you say 2?
Well,
Yeah, it's the second one, yeah, but it starts at, yeah, so boron starts the 2 Ps, and then the aluminum starts the 3 Ps. Okay. So boron, that group's already full. And we can't have a 1p. Why can't we have 1ps? This would be a great exam question too. I don't see a 1p subshell. Why not? What?
Because such configuration does not exist.
It doesn't exist, but it can't, according to the quantum numbers. The quantum number, like, what do I want to say? The quantum number sets, the rules, it can't exist. Where's the rule that says it can't exist? I've written it on the screen down here. This n minus 1, the maximum L value is n minus 1. So for a 1s orbital, n is equal to 1. And so L, the full set, it starts at 0 and goes all the way up to n minus 1. And n minus 1 is 0. So we can only have an s orbital for the first shell. So that's why there's no 1p's. Okay. And that's also why there's no 1d's, because L is, if it's a D, L is equal to 2, and we can't have a 2 if n is 1. So that's what limits. So then we row 2, now we have an L equals 1, and so we could have a P subshell for the second row, but we can't have a D subshell. So the very first D subshell comes in at n equals 3. So this one right here is neon, and then the very first one was the 3p. What's the next available? So this whole column is np, so something p. And so if this is the 3p, then this is going to be the 4p. So 4p, 1. Okay, so that's your electron configuration for that atom. It has all of those electrons in the neon subshell plus that extra electron that's in the 4p subshell. And I have you do all, that's what this question's about, all of these different ones. So state 3, that's the 3p one, that's this one right here. For state 5, we're over here now, we're in the D's. Okay, so it can't be this one, can't be that one, can't be that one. I mean, this is the only one, 3D. That's the first available D shell, and this is the lowest energy one in the D column. Okay. Okay, what frequency and wave numbers corresponds to the transition from 2 to 3? Okay, so if we had a transition from 2 to 3, this one is, it's a little bit above 25,000. This one's, what, about 17,000? Okay. So what is that, 14,000? Oh, 2 to 4. I'm sorry, I'm not reading the question correctly. 2 to 4. It's approximately 5,000. They're both a little bit above. This one's coming in a little bit above 30,000. So I would take this one. Y'all see that? You can just look at that y-axis, and those are all energies. They're in wave numbers. What if I asked you if that was in the visible region? How would you answer that question? So this is 5,000. 5,000 wave numbers. And that's equal to 1 over lambda, when lambda's in centimeters. Okay. So what we want to do is we want to solve for that that wavelength, right? And so 5,000 per centimeter, we could put the centimeters on top. Is everybody cool with that? Oh, not -1, just centimeters on top. Is everybody cool with that? Okay, so let's now do the conversion from centimeters to nanometers. Now I want to show you a trick I teach my freshmen. So I want to go out of centimeters and I want to get to nanometers. The centi, what is the power of 10 for the centi? 10 to the minus 2. What about nano? 10 to the minus 9. So I'm multiplying by 1. It's just a unit conversion. So I do the nano 10 on bottom and the centi 10 to the minus 2 on top. And so we can simplify this. If I were to bring this, see, I'm dividing by 10 to the minus 9. If I bring it up on top, what do I have? 10 to the 9th. So this is plus 9 here. 10 to the minus 2 plus 9. So that's 7. Is everybody cool with that? So I just take 10 to the 7 and divide by 5,000. And that gives me my wavelength. Pull up my calculator. But that should, I mean, eventually if you do it a lot, you just remember 10 to the 7 divided by whatever number in wave numbers. So 7, 5,000. So 2,000 wave numbers. I mean, sorry, 2,000 nanometers. And so my question was, is that in the visible region or not? No, yeah, I just did the color lab. So you know the visible region, don't you? What is the low end and high end? 400 to 700. Yeah, that's great. Which one is blue? 400. Which one's red? Yeah, that's great. And Roy G. Biv in between. Okay, so great. Next question. A spin. Yeah, so here's some term symbol questions. So let's say if I give you a term symbol, I'll give you a crazy one, okay? Like an F, a quartet F. We have triplet, singlet. When you get doublet, we get to four. What is it? It's a quartet, just like in music. What about five? Quintet. Yeah, that's as high as I've ever seen. But so this is the multiplicity. Multiplicity, which is equal to 2s plus 1. Okay. And so we just solve for s. S is that spin. Okay. So 4 minus 1 divided by 2 is equal to s. I did a little bit of algebra there. So if 4 equals 2s plus 1, we subtract 1 from both sides, divide by 2, and we get s. So it's 3 halves. And we can just leave it at that, that s is equal to 3 halves. Because we have a lot of times listed, if I have 3 halves, what have I got? I've got 3 unpaired electrons, a 1/2, a 1/2, and a 1/2. So that's why we like to leave things in 3 halves, 5 halves, and so on. It's kind of like counting up how many electrons you have. We know we have 3 electrons unpaired, and that gives us three halves. Okay, so that's the spin. And so then when you're doing the J quantum number, you have L plus S and L minus S and so on. So the J quantum numbers for this quartet F would go from L minus S all the way to the absolute value of L plus S, sorry. L plus S all the way down to L minus S, absolute value. So let's do the maximum value. So what is L, capital L, for this crazy quartet F? I use my fist thing. So S, P, D, F. So L is 3. So we have 3 plus 3 halves. Okay. And so it'd be easy if I could just make it all halves. Okay, so let's just, if I could rewrite 3 in terms of halves, what would it be? 6 halves, right? So we'll start with that. We'll say 6 halves plus 3 halves. Right? And so that's going to be, my maximum value is going to be 9 halves. And then I'm going to subtract 1 from that. Let's do our minimum value. Okay, so we have over here 6 halves minus 3 halves. So that low end value is going to be 3 halves. Does everybody agree with the maximum and the minimum? Okay. Now we're subtracting 1 from all of these. So when we subtract 1, but we're still staying in halves, how many halves do I subtract if I'm subtracting 1? 2 halves. So I'm going to go to 7 halves. Okay. And I'm going to subtract 2 more, 5 halves. And then when I subtract 2 more, I end up with the 3 halves. So those are my 4 J values that I would have for a quartet F. We kind of jumped into the middle of the problem, but that's okay. That makes it a nice short problem. So this is totally legit. I could give you something crazy like this on the exam, and it's way easier than you think. Like you're going to look at this and go, holy cow, I've never seen a quartet F. I don't know what he's talking about. What if I gave you a quintet G? Oh heck, what am I going to do? S, P, D, F, G. Okay, L is 4. I can do that, And then quintet, what at 5? That's the multiplicity. And so then you could solve for S and do this whole thing. Yeah. So we would write these terms out if we wanted to show them all. Quartet F, 9 halves. Quartet F, 7 halves. And those would be the hyperfine splittings, and that electron configuration with 3 unpaired electrons and the f orbital or something like that. Then you would have these little hyperfine splittings, which would have all of the little electrons up and down in the f orbital, adding and subtracting their tiny little magnetic fields and giving you different energies. So that's what all of these terms are. Great. y'all just don't know what you're missing. When I had to do this, our professor had us draw all the little pictures. You had the f orbital, which is 7 f orbitals, and you had to put the electrons in them, and you had the m sub l numbers, and you had to add up a half to the m sub l and subtract a half and all of that. And you drew so many little pictures. It was a whole page of little pictures of spin ups and spin downs, and you never knew if you got all the terms. So you had all these pictures, and some pictures were just the same picture you had written twice, and so you screw that up. And then some pictures you just forgot because you didn't. There was no systematic way to draw all of the combinations. And so when I learned the Clebsch-Gordon series, these 3 series, you're guaranteed to get all the terms, and it's not very pictorial. Like you can't see the electron in the orbit adding its plus spin or down spin, up or down spin, but you're guaranteed to get all of the terms and all of the energy levels. And so it's tedious, but it's guaranteed to give you all the answers. So I don't know why they didn't teach it to me. I didn't learn until grad school. So there's a lot of stuff in this course like this that really is in grad school that I'm kind of squeezing into you guys. Okay, so you're better at atomic spectroscopy for it. Yes. Yes. 11. There you go. Okay, so this one, some of these, and maybe I did, maybe I should, I mean, I don't know, maybe I'm not helping you very much because, when you've got just a single electron in there, the Clebsch-Gordon series is almost too simple, right? You don't have an L1 and an L2 to add. You just have an L1. Okay, so we have that one electron in the p orbital. So big L is just equal to little l, L1. We don't have an L2. Okay, and so SP, so the L is equal to 1, and so the big L is equal to a P, capital P. So that's our big letter for L. And so it's not going to be, by process of elimination, if you're on the exam and you're going quickly, right, you got down to two options. Yay. All right, so then we can know that we only have one electron, and so it's going to be, we start with spin up. So this S is 1/2. Capital S is equal to little s1 plus little s2, but we don't have any little s2, so that's equal to 1/2. Okay. And 2s plus 1 is the multiplicity. Okay, so that's going to be 2. It's going to be a doublet. So we got doublet P. Okay. And then J is equal to L plus S down to L minus S. Okay, so 1 plus 1/2 is 3/2, and then 1 minus 1/2 is just 1/2. And if I take 3/2 and subtract 2/2, I get 1/2. So this is the full set. I just put my big comma right in the middle, so that's my J values. And so it's the doublet P 3/2 and the doublet P 1/2. Yeah, so it's this one. And so the only difference between these is there's no, this singlet idea, there's no, there's only one unpaired electron. And so this is the error on here. It's not a singlet P 1/2, it's a doublet P, because the multiplicity is the number of unpaired electrons plus 1. So we have one unpaired electron, so you add 1 to that, you get a doublet. So that's how you do that one. But it's almost too simple because we don't have to add L1 and L2 because there's no L2, or S1 and S2 because there's no S2.
What would the setup look like if there was like an L1 and an L2?
Go to the notes and do the carbon one, the P2 in the carbon. That's a good example. because we have two p orbital electrons, and so L1 and L2, you take the quantum numbers for each electron and add them together. So L1 for a p electron is 1, and then the second electron's in the p orbital, so it's 1. So you have 1 plus 1 all the way down to 1 minus 1. And so that gives you your big letters. You have, yeah, it's all right there in the notes we walked through carbon, the P2 system. I guess where it could get interesting is if we did an excited state one, still with 2 electrons. So let's do that. Make it interesting. Tablet working. All right, so we're going to do, let's just take carbon and excite one of those electrons. Okay, so carbon, now I'm going to go ahead and write out the full electron configuration. So carbon is on the second row, so helium is its core. First 2 electrons are taken up by helium. And then we have the 2s, 2, and then the background state is 2p2, right? But we're going to have a 2p, and then do y'all want to do a 3d? That's the first available d orbital, or a 4f, the first available f orbital? F, let's be adventurous. Okay, 4f. So we got an excited carbon atom with an electron in an f orbital and an electron in the p orbital. So let's come up with the term symbols for this guy. All right, so we'll do L first. L. All the way down to L1 minus L2, absolute value. So this whole absolute value thing too is a way to eliminate the fear that you are going to choose the wrong electron for L1 and the wrong electron for L2, right? So we don't have to worry about that. So we're going to start here with L1. So it's in, the first electron is in a p orbital, okay? sp, so that's L equals 1. And then the next one's in an f orbital, s, p, d, f. So the 3, so L equals 3 there. Now you see where the absolute value comes in, right? Because if we had written it the other way, it'd be 3 minus 1, and it'd be positive. But we wrote it 1 first and 3 second, and so the absolute value comes into play. So what is 1 minus 3? That's negative 2. We're going to make it positive 2. So we just need the absolute difference between the two. So we have a 2 here. So this one is going to be a 4 and 2, and I could subtract 1 from 4 and get 3, and subtract 1 from 3 and get 2. So those are my 3 L values, 4, 3, and 2. Now we go back to letters. This is capital L, so we need the capital letters. So SPD, so 2 is equal to a capital D. F is 3, so and then G. SPD, F, and then G. So we're going to have a G, F, and a D. Those are our letters. You could even write them if you wanted in like a little set, because those are sets. Even though they're letters, they are representing numbers for the angular momentum. Okay, then we do S. Little s plus S1 plus S2, all the way down to S1 minus S2, absolute value. 1/2 plus 1/2. I didn't ask you how to get that. Where'd the 1/2s come from? These are the spin quantum numbers on my electrons. And so we're going to start with both of them up, and then we'll let the Clebsch-Gordon series determine them. When one's up and one's down, then they cancel out. And that's what the minus part is. So this is going to be, 1, and this is going to be 0. So this is equal to 1 and 0. So when you subtract 1 from 1, you get 0. So there's only 2 terms here. Okay. So that's capital S. Multiplicity, 2s plus 1 is equal to the set of 3 and 1. So 2 times 0 is 0 plus 1 is 1. And 2 times 1 is 2 plus 1 is 3. So we got triplet and singlet. So we take a triplet and a singlet and we put it on the G. So we have triplet G, singlet G. We have a triplet F and a singlet F. And we have a triplet D and a singlet D. Now we have 6 different problems to do. Okay. Where I don't have enough space. Next page, right? So, but this is, we take one of these, and so let's do let's do the triplet G, because that's the largest one, and we'll see if that's going to be enough to satisfy you so we don't run out of time. Okay, so for the triplet G, we have J equals L plus S down to L minus S. Okay, G is 4. We don't have to do my little fist or anything because up here we have that right there on the page. We look up there, G is 4. So that's L. So 4 plus, and we're doing triplet, and that means the S is 1 for a triplet. So this is S right here. So 1, 4 plus 1 all the way down to 4 minus 1. So 4 plus 1 is 5. Okay. 5, 4, 3, and then 4 minus 1 is 3, so we're done. So we have 5, 4, and 3. So our 3 terms for the triplet G would be a triplet G5, a triplet G4, and a triplet G3. There you go. Question? Yes.
Just to confirm that our first J, the L plus S, it would be 4 plus 3, our first S?
It's 4 plus 1 because S is 1 here. That's a common mistake. So this is S. The 3 is 2S plus 1. That's the multiplicity. Now, I've never seen a letter given to multiplicity. So we don't, we have L, we have S, we have J, but there's never a letter that I've seen in the textbooks or anything given to multiplicity. Maybe we should come up with one, but a lot of them are taken, and I don't want to confuse you. Like if I start calling multiplicity M, but then we also have the M sub L and we have the M sub S, what is M? So, I mean, maybe we could make a set that says the multiplicities are called M or something like that, but that would just be me interjecting that, and you would never see that in the literature. So I don't know what to call multiplicity except to use the whole word. So the multiplicity is 3, but S is 1 for that. Yeah. Okay. It's strange. They put letters on everything, and yet I've never seen one for multiplicity. So yeah, we could. Yeah. Mm-hmm. Yeah. Okay. What else? What other questions? Yeah. I'm self-conscious about my chicken scratch. I hope that y'all can read it. At least on the video, I'm talking about what I'm writing. So you're like, oh, that's a 2. I'll take his word for it. For the stuff like this point group, I mean, this is the tetrahedral point group for titanium and so on, but I didn't have you in the homework, come up with it. Um, I haven't thought about it. Yeah. I see some no's. That's fair. Yeah, so we'll just go. Here's what I've got for the exam. This is a little deal I put on here. So quantum numbers, N, L, M sub L, M sub S, electron configurations, lower state, upper state, excited states. And then we get into the electronic spectroscopy, the fates of the excited states, right? So what do I mean by that? What's the fate of an excited state? It's like a fortune, right? Fluorescence, yeah. Someone else? Phosphorescence, yes. I thought you said false fluorescence. Phosphorescence. I need to clean my ears. Yeah, it is kind of that. Yeah. So those are which ones are those if you were going to put them in a bucket? Yeah, radiative. Very good. Yeah, radiative fates. What are the non-radiative fates? Intersystem crossing, internal conversion. Those are where they hop from what to what? From different potential energy surfaces. Yeah. And you need to know whether that's the same multiplicity or different. Yeah. There's also just non-radiative relaxation, like it just percolates down through the vibrational levels. Um, so it does that plus intersystem crossing a lot of times. So it'll non-radiatively relax, and then it'll do perhaps an intersystem crossing where it changes multiplicity, or internal conversion where it does not change multiplicity. And it can sometimes work its way all the way down to the ground state and just give off heat. So that's the fate of the excited states. Duel of the fates. And then Grotrian diagrams, which we were just working with. And then term symbols, which we were just working with. And then Jablonski diagrams and the relationship to the spectrum. So what do I mean by that? Well, do I have a figure on that? I think I do. Let me scoot ahead. Oh, these are propagation of uncertainty. I had some questions about that from the CO lab. So here's the Grotrian diagram, but let's look here at there's a practice exam on Blackboard, so go look at that. This is the figure. So this is a Jablonski diagram that looks a little different than the one in the notes. And so I wanted to put that in your hands because I think it confused. The very first time I made this one myself. Yeah, pat. And so, but it looked enough different from the one in the notes that the students on the exam were like, I don't understand. It's too different, right? And it was just because this S0, was wide enough that it was completely under S1 and T1, But this is a totally legitimate Jablonski diagram. Remember, the only accurate points on this Jablonski diagram are the minimums of these. So these are accurate. These come from spectroscopic measurements. So you'd have, a spectroscopic measurement of a peak at some wavelength that would correspond to 22,000 wave numbers for this emission line, and then maybe another one that corresponded to 2,000 wave numbers for this triplet state, maybe a phosphorescent transition here, and that would come in at 2,000. But as far as these vibrational modes, vibrations, energy levels, energy. They're just scribbled in there because the Jablonski diagram is about visible spectroscopy, not about the vibrational spectroscopy. So the vibrational stuff is just in there, and it's just demonstrates we have non-radiative relaxation and heat. We're not detecting that. We're in the visible region of the spectrum, and so we would consider that non-radiative. Even though it's emitting infrared light, we're not interested in infrared when we're doing visible spectroscopy. So we don't have those accurate things. And so we just draw these non-radiative paths, like path 1. If I were to ask you on a multiple choice, which one of these paths is non-radiative relaxation? You're going to pick path 1, right? Because path 3 is a certain kind, path 4 is a different kind. Also, looking at this, it's color coded, and the UV light comes in, UV and blue light comes in, and that gives us a singlet to singlet transition. We're going from S0 to S1. And so how does that relate to the spectrum? That's going to be this piece right here. So this is the emission or the absorption line. So this UV light, that's going to be right here. That's absorption. And then we're going to see emission here. This one is fluorescence, path 3. And this one here is path 4.
Vibrating and releasing heat at the back.
Ask it again. Yes, and then what happened for path 2? Which type of non-radiative fate is that, path 2? Yeah. Intersystem crossing, yes. Because why do you say the intersystem one? S and T, singlet and triplet. So if it's going from singlet to triplet, then it's an intersystem crossing. Yeah. And why are we not using the what we just used for term symbols, you know, the prefix superscript of 3 and 1? Because people in UV vis, molecular spectroscopy, didn't talk to the people doing atomic spectroscopy. Okay, and so they just use a big capital S for singlet electronic potential energy surface in UV vis, and the atomic, the physicists, it really is two camps. The atomic spectral database was made by physicists, and this stuff is made by chemists, and so they just didn't talk when they made their typical, you know, things. I mean, it would be way better if we had like some kind of term for the molecular potential energy surface and use the same little deal, you know, superscript prefix triplet for triplet states and superscript prefix singlet for singlet states and doublet states and all of that stuff. So you, even on the same exam, you've got to do some code switching. Am I talking about a Jablonski diagram? Now I'm talking about a capital S as a singlet and the capital T is a triplet state. Yeah. And this is I don't know, it's such a small little detail, but if you don't get it, you're gonna like not know how to interpret one of these things. And so that's why for me, I look at all of this stuff because I know all these little details and it seems incredibly easy for me. And if you miss that, you're going to be looking at it going, I don't know if this is a singlet or a triplet. I don't have my little superscript. Where's my 3? Where's my 1? Right? And so that's, I guess that's why you got to come to class and like focus, because there's a lot of little details. But there's nothing hard about that. You just got to memorize it or you know, learn it some way. Yeah. So this is, I didn't draw my little, so this is 700 nanometers. This is 400 or 300 if it's UV light. Relative intensity. Why did I say that and not absorption? Because I only have one absorbance peak on here, and these are emissions. So these are not absorbances. So we can't plot an emission peak on our spectrum and call it absorbance because it's emitting light, it's not absorbing light. So we have to, if we're going to plot these on the same plot, we have to say relative intensity or signal or something like that. And then we can plot everything on the same plot. That's it. Okay. Propagation of uncertainty, we're going to do that in the CO lab, and you guys are going to be graded on it that way. So, but this is just, it's on the video, so you can see the propagation of uncertainty here. Okay. We got 5 minutes still. Keep going. Other questions? I'm thinking if this is in the exam review that it's going to be on the exam. We had it on the homework, right? The relative standard deviation, the RSDs. We had it on one of the homeworks, I know, because it was like if the RSD for the bond length is this, what is it on the rotation constant and so on. What's that? Was for the last exam? Yeah, okay. Yeah, rotational constant. Yeah, rotational constant calculation, propagation of uncertainty. So that's what I'm showing here. So we've got these RSDs. This is a thing that you have to absolutely have to know. The RSD is this piece right here, right? It's that's again, RSD is the uncertainty over the value. So if I have, the average equals 56.3 and the standard deviation equals 5.6. Okay, I'm going to do it so I can do the math. The RSD is equal to 5.6 over 56.3. Okay, which is about 1/10. So 0.1. If I multiply that by 100%, I get 10%. So that's the coefficient of variation, CV. If it's a product, you can have this really complicated formula, and y'all get your note cards, right? But this is just a simplified version of that. You see, if I brought y over here and I squared it, then I would get rid of the square root, right? So the relative standard deviation for y squared is equal to the sum of all of the pieces, all of the RSDs of the pieces squared. So that's what this simplified equation is telling us. Okay. And then if it's addition and subtraction, again, if I squared both sides, I would get rid of this, and I would have the variance. This is the variance of the result is equal to the sum of the variances of all the things that were added and subtracted. Okay. If we have a special case of multiplication, which is just exponentiation, if I had 3 of these pieces, like if I had a cubed, it would be the RSD for a squared plus the RSD for a again, plus the RSD for a third time because it's cubed. And so why not just multiply that by the exponent? And so it's the RSD of a times the exponent gives the RSD of the result. And so I'm just moving y over here. So that's what we're showing. The RSD of a times the exponent gives RSD for the result. Now that comes in also for square roots. And so if we're doing the bond length, we solve for the bond. Do I have that on this screen? That's just, it's the same kind of thing because this is the force constant. And so we're solving for K, and K is inside the square root. So when you rearrange it, you end up with, where is it? K here. K is all of this. And so we have this frequency squared. Okay. And so the uncertainty in that is going to be K times that square, that's the 2 right here, times the RSD in my vibrational frequency. So this RSD in my vibrational frequency, this is S nu, and this is nu. So that's where those two numbers came from. So that's how you do the propagation of uncertainty for the force constant. And so if I give you an ANOVA output and ask you to propagate the uncertainty for K or for the bond length, you should be able to do that. Okay. All right. Last one. All right. Y'all do well, okay?